Hello dear students, welcome to another class on analog and digital electronics. Today, today we are going to just have a recall on what we have studied so far. So the topic covered so far are photodiode, LED and photocouplers. Also the topics to be covered in this session are the BJT biasing. There are three types of biasing: base bias or fixed bias, collector to base bias circuit, and voltage divider or emitter current bias circuit. Let us look at what is BJT biasing. BJT stands for, or it is also called as a transistor. It stands for bipolar junction transistor. It is a sandwich of one type of semiconductor, that is P type of N type, between two layers of another type. Transistors are of two types, that is PNP transistor and NPN transistor. There are three distinct regions or terminals in a transistors, that is emitter, base and collector. So this is a transistor. The arrow indicates emitter. I'll write it as E. This terminal is a collector. And this terminal is called as a base. Okay, so the basically which type of transistor I have drawn is the NPN transistor. So this is NPN transistor. All right. Right. So moving on, for any circuit, 4 terminals would be required. Okay, two input terminals and 2 output terminals. Hence, for a transistor, one of the 3 terminals will be common to both input and output in a circuit. Thus, there are 3 different modes of operation for a transistor, that is common base connection, common emitter connection and common collector connection. Okay. Now, transistor biasing is the establishment of suitable DC values such as IC, VCE, IP, etc. by using a DC source. So this is a transistor. As I've told you, this is the base, this is the collector and this is the emitter. Okay. Now, transistor biasing is nothing but it is an establishment of suitable DC values such as IC. So whenever you establish a current at this terminal, that is the collector terminal, it is called as a IC. Okay, the current across the base terminal is called as IB, and the voltage across this the collector and the emitter is nothing but this one. You establish this by giving the input, DC input. Okay, so this is the collector emitter voltage. Okay, so by using a DC source, for example a battery as example, okay, you give the this transistor these inputs, that is IC, IB and VCE, so that you get an amplified version of the output. So transistor basically it is used for the amplification purpose, right? So by applying these voltages, it is applying these voltages is also called as biasing. Okay, biasing is nothing but an establishment of suitable DC values such as IC, VCE and IB by a DC source. Okay, when BJT is properly biased, amplification of signal takes place. Okay, so when proper voltages, that is IC, VCE and IB are given to this, it acts as a amplifier. Okay, so there are basically three types of biasing a transistor. Okay, three main types of biasing a transistor, that is base bias, fixed bias, and collector to base bias. Okay, and also base bias, it is also called as fixed bias, collector to base bias, and voltage divider bias. Okay, so let us discuss what is the base bias or fixed bias. Okay, base biasing configuration is given in the following figure. So what happens in the base bias is see, you can see that we require two inputs and two outputs terminals. So the emitter and the base are acting as a input here, and collector and the emitter are acting as a output. Okay, so common is emitter. Okay, so it is grounded. Okay, so whichever the terminal common, whichever the terminal which is common is grounded. Okay, so base biasing configuration is shown here. Okay, where we are applying the input to the base. Okay, so the base resistance RB is used between VCC and base to establish a base current IB. Okay, so to establish a base current, we are using the resistor RB and the voltage VCC, that is the input voltage. Since VCC and RB are fixed quantities, the current IB, it remains fixed. Okay, now when we apply the Kirchhoff's voltage law to the base circuit, okay, so what is the base circuit? This is the base circuit. Okay, when we apply the KCL to this loop, okay, we get VCC minus RB IB RB. See, always the terminals are like this, positive and negative. Okay, so we are going in the opposite direction of the flow of current, so it is minus RB RB IB RB minus VBE. See, again this is the direction of the current which we are considering, which is nothing but the opposite to. See, whenever the direction is from going from positive to negative, it is taken as negative. Okay, the direction is taken as negative. Okay, so when you apply the KVL to this base circuit, what you get is VCC minus IB RB minus VBE. So this is VBE. Okay, so this is VBE. Right, so this is equal to, see, KVL, it states that the voltages, the sum of voltages and the potential drops, or the product of current and resistor, is equal to 0. So that is equal to 0, or you can also rearrange this as IB is equal to VCC minus VBE divided by RB. Okay, considering this as the equation number 1, applying KVL to the collector circuit. Okay, so when you apply the KVL to the collector circuit, what you get is this. Okay, this is the collector circuit, that is VCC minus ICRC minus VCE. Okay, so that is this circuit. Okay, so this circuit you are applying. Okay, so you get this one equation. So when you rearrange it, you get this equation, that is VCE is equal to VCC minus ICRC. Note that the voltage and the current polarities are reversed in bias circuits of NPN and PNP transistors, but the same KVL equations are applicable. Okay, so this is the NPN transistor. So how do you identify which is PNP and which is NPN transistor? See, whenever the emitter, this arrow indicates the emitter terminal, right? So this is the emitter, this is the collector, this is the base. Okay, base always with this input, okay, line. Okay, so whenever the emitter terminal is pointing outward, out of the direction of the base, okay, so it is called as a NPN transistor. Okay, as the name only indicates, not pointing in. Okay, to remember, you can remember like this, not pointing. Okay, that means the arrow is not pointing towards the base. Okay, wherein this is the PNP transistor, which is pointing in. okay, pointing in transistors. Okay, just to remember, you can remember using the names like that. Okay, so this is the NPN transistor base bias, and the corresponding PNP transistor base bias is this one. All right. So whenever the transistors are connected in this way, it acts as an base bias or fixed bias amplifier. Okay, so let us solve a problem based on this base bias circuit. Okay, we saw we have an equation for the base current, that is the input current, and we have the equation for the output voltage, that is VCE. Okay, now the base bias circuit is shown in the figure. For the values indicated, calculate IB, IC and VCE. So we have to calculate the base current, that is the input current, the collector current, the output current, and the VCE, that is the output voltage. Okay, so you have these values given, that is IB, RB, RC and VCC. Okay, IB is nothing but the equation which we have already done here, that is VCC minus VBE divided by RB. So when you substitute the values here, you get the input current as 36.8 microampere, and IC is nothing but the collector current. It is given by the formula HFE IB. Okay, so HFE is given. See, HFE is nothing but the gain of the transistor. Okay, so the gain of the transistor is 100 here. So gain into IB. IC is nothing but gain into IB. So 100 into 36.8 microampere, that is equal to 3.6 milliampere. Okay, so VCE is nothing but VCE minus RC. So here we have calculated VCC minus RC. So this should be VCC, okay, minus RC, that is equal to 18 volt. Okay, so that is equal to 18 volt minus 3.6 milliampere into 2.2 kilo ohm, that is equal to 9.9 volts. Okay, in the next example, so you have the input voltage and the output voltage, that is VCE, that is equal to 9.9 volt. Okay, next, calculate the maximum and minimum levels of IC and VCE for the base bias circuit in the figure A. Okay, so this is the figure, and there are two gains given, that is minimum gain, that is 50, and maximum gain, that is 200. Okay, so this is the circuit. We have to find out the values of IC and VCE for two cases, that is when minimum gain and maximum gain. Okay, so given this is the given values are HFE is equal to 50, HFE max is equal to minimum is equal to 50 and maximum is equal to 200. IB is equal to VCC minus VBE upon RB. Okay, this is the equation we have already derived. Okay, so that when you substitute, you get 36.8 microampere. Now when the gain is 200, what is the collector current, that is IC, that is equal to 200 into this much, so that is equal to 7.36 milliampere. So what will be the VCE? VCE is nothing but VCC minus RC. So that is equal to IC that is equal to 18 minus 7.6 milliampere into 2.2 kilo ohm, that is equal to 1.8 volt. Similarly, when you calculate for HFE minimum, that is IC is equal to HFE into IB, the 50 into 36.8 microampere, that is equal to 1.84 milliampere. So therefore you get VCE as VCC minus RC, that is equal to 18 minus 1.84 milliampere into 2.2 kilo ohm, that is equal to 13.95 volts. Okay, so the two Q points in figure C for a transistor of a given type number always have a wide range of HFE values. Okay, so there are two Q points. Okay, one here and one here. Okay, so they have a wide range of whenever there are two Q points, they have a wide range of the gain values, that is HFE spread. Okay, so HFE max and HFE min should always be used for the practical circuit analysis. Okay, the base bias circuit is rarely employed because of the uncertainty of the Q point. So the Q point either can be here or it can be here, okay, or it can be in any two other points, okay. Because of the uncertainty of this Q point, okay, more predictable results can be obtained with other types of bias circuit. Because of this Q point existing in different regions, okay, this base bias circuit is not usually stable, okay. Hence more predictable results are obtained with other types of bias circuit. This is not usually used. Base bias circuit is not usually used, okay. So the Q point for HFE, when the graph is drawn for this example, okay, for 200 it is 7.36 milliampere, and when the gain is Q point at HFE, that is 50, that is the current is 1.84 milliampere, okay. So the corresponding voltages are 1.8 volt and 13.95 volt, okay. Similarly, when in the previous case, when the HFE was 100, the voltage was 9.9 volt. So this is when HFE is equal to the Q point is equal to 100. Next bias circuit which we have to consider is collector to base bias circuit. The collector to base bias circuit shown in the following figure has the base resistor RB connected between the transistor and the transistor collector and the base terminals. So when RB is connected between the collector terminal and the emitter terminal, the base terminal, then you have what is called as a collector to base bias circuit, okay. This circuit has significantly improved bias stability for HFE changes, okay, compared to the base bias, okay. So whenever the HFE, that is, see, HFE is nothing but the gain, okay. The gain of a transistor keeps on changing. Whenever the gain keeps on changing, the previous circuit, that is the base bias circuit, is not stable, okay. But whereas this circuit, that is the collector to base bias circuit, is more stable when the gain changes, that is the HFE values changes, okay. So when you apply the KVL to this outer loop, okay, so this is the outer loop, okay. So VCC, okay, this is the loop, okay. Whenever you apply the KVL to this, VCC minus, see, look at the direction, it is going from the positive to negative, so we are taking it as minus, okay. Whenever the current is going from, whenever the current direction is going from positive to negative, it should be taken as minus, okay. Minus IC plus IB into RC minus VCE, okay. So I'm sorry, this is not the loop. Okay, so this is the loop we are talking about, outer loop, okay. So VCC minus IC plus IB into RC minus VCE, okay, is equal to 0, or you can rearrange it as like this. Applying KVL to the loop VCE, IB, RB and VBE. Now this one, okay. When you apply the loop here, you get VCE is equal to VBE plus IB, RB. So this is nothing but VCE minus VBE. So the loop is this one, okay. So you are applying the here, okay, VCE minus VBE minus RB IB RB. Okay, so you are taking here, okay, from this you can see that the current is in the this direction, that is going from minus to plus, so it is positive. Okay, VCE minus VBE, okay, minus IBRB, that is equal to 0. When you rearrange, you get this equation. Equating equations 3 and this one, because both are VCE only, you get IC plus IB into RC plus IBRB is equal to VCC minus VBE. Okay, so when you rearrange it, you get this equation taking IBRC common. Okay, so the common factor between this and this is IB, right? So when you take, you get this one, okay, plus ICRC is equal to VCC minus VBE. When you substitute, IC is equal to beta IB. See, HFE, which I was considering in the previous example, okay, that is also called as beta. Okay, so beta IB in above equation, when IC is equal to beta IB in above equation, we get this equation. Okay, that is when rearranged, you get this equation. Okay, now effect of IC on beta. Okay, whenever the collector current changes, it affects something. Okay, so any changes in the VCE changes IB. Okay, whenever the collector emitter current voltage changes, it changes the base current. Okay, the change in the base current causes the collector current, that is the output current, to change. See here, whenever the collector emitter current changes, that is this changes, whenever the voltage VCE changes, okay, whenever the voltage VCE changes, okay, it changes the IC, that is the collector current. Okay, whenever the collector current changes, it changes the IB, where VCE changes IB and IB internally changes IC. Okay, because IC is equal to beta IB. Beta IB, right? So if IC changes in the above design level, there is an increased voltage drop across RC. Okay, when IC increases, there is a drop across, increased voltage drop across RC, resulting in the reduction of VCE. Okay, the reduced VCE causes IB to be lower. Okay, that is the whenever the IC increases, it increases the voltage drop across RC. Whenever the IC increases, see what they are telling is, if IC increases, okay, above the design level, there is an increased voltage drop across RC, resulting in the reduction of VCE. So when IC increases, okay, when the collector current increases, there is an increase in the voltage drop across this IC RC, across this resistor, okay, which will change or which will reduce the VCE. Okay, this reduced VCE causes reduce IB. Okay, this VCE, whenever it is reduced, it will reduce the IB. Okay, if IB increases, then IC also decreases. Okay, as IC is equal to beta IB. Okay, so when IB it reduces, it will reduce IC also, because IC is equal to beta IB. Okay, so if IB decreases, IC also decreases, as IC is equal to beta IB. Okay, similarly, a reduction in IC produces an increase in VCE, which increases IB. Okay, thus tending to increase IC back to the original level. Okay, thus an increase or decrease in the IC produces a feedback effect that tends to return IC towards its original level. In the collector to base bias circuit, the feedback from the collector to base reduces the effect of beta due to transistor replacement. Okay, thus the collector to base bias has greater stability than the base bias for a given range of beta values. In the next uh, bias circuit, we are going to discuss the voltage divider or emitter current bias circuit. The voltage divider bias is the most stable of the three basic transistor biasing techniques. Okay, the voltage divider circuit is shown in the following figure. That is this one. Okay, there is an emitter resistance Re which is connected in series with the emitter terminal. Okay, so that the DC load in series with the transistor is RC plus Re. So what is the DC load? This is the output side, right? So this is RC plus Re is the thing but the load. Okay, the resistor R1 and R2 constitute a voltage VB. So what is the base? That is a input voltage, that is it is nothing but by the resistance R1 and R2. Okay, so it constitutes a voltage VB. Applying KVL to the loop VCC R1 and R2, we get, so when you apply the voltage KVL at VCC R1 and R2, we get VCC minus I1 R1 minus I2 R2 is equal to 0. That means this loop. Okay, when you apply the voltage at this loop or KVL at this loop, you get this one. Rearranging, you have I1 R1 plus I2 R2 is equal to VCC. Okay, now I1, what do you mean by I1? I1 is this one. So here is I1. So I1 is going like this. So I1 is nothing but, it is nothing but IB plus I2. Okay, so or I2 plus IB. Okay, I1 is equal to I2 plus IB. Okay, now voltage divider bias circuits are normally designed to have a voltage divider current I2 very much greater than the transistor's bias current transistor bias current IB. Okay, so they are this voltage divider bias current are designed so that the I2 is very much greater than IB. That is written here. Okay, so when I2 is greater than IB, hence I1 will be equal to I2. Okay, because I2 is very much larger than IB, so we can neglect this. Okay, so I1 will be equal to I2. So when you use this equation number 6, that is I1 is equal to I2 in this equation, okay, you get I1 I2 R1 plus I2 R2 is equal to VCC, or you can take I2 common, you get I2 in the bracket R1 plus R2 is equal to VCC, or you can also write I2 by bringing this down, that is VCC divided by R1 plus R2. Now here VP is the voltage across R2. Okay, so what is the voltage across R2? That is VP. Okay, that is VP is equal to I2 R2, or you can also write it as I2 by substituting I2 in as this one. Here you get VCC divided by R1 plus R2 into R2. Okay, so you are just replacing I2 by this equation. Okay, so VE is what? VE is nothing but voltage across the resistor RE. Okay, this is nothing but VE is equal to IE RE. Okay, now when you apply the KVL to the base emitter loop, Okay, so this is the base emitter loop. Okay, when you apply the KVL to the base emitter loop, what you get is this is the base, this is the emitter. Okay, so VB minus VBE, so this is the base emitter loop, that is nothing but the VB, that is the voltage across this R2, minus VBE, that is this one. Okay, the base emitter. Okay, VB is nothing but the voltage at the base, VB minus VBE minus the voltage at the emitter, that is VE. Okay, that is equal to 0. So you have VBE is equal to VB minus VE, alright, or VE is equal to VB minus VBE, that is nothing but when you substitute VE is equal to IE RE over here. Okay, you get IE RE is equal to VB minus VBE. Okay, hence emitter current is nothing but VB minus VBE, that is a base current, base voltage minus the base emitter voltage divided by RE. Applying KVL to the collector emitter loop. Now when you apply the KVL to this circuit, okay, this loop, okay, what you get is VCC minus RCIC alright. So when you apply the KVL to the collector emitter loop, okay, so you have VCC minus ICRC, okay, minus VCE, so this is nothing but the negative direction, okay, minus VCE, okay, minus ICRC RE, that is this one, the voltage drop here, okay, that is equal to 0. Okay, when you rearrange this, you get VCE is equal to VCC minus RC into RC plus RE. Okay, so this is nothing but the input voltage and the output voltage. So the VCE is nothing but the output voltage here. VCE is equal to VCC minus IC RC plus RE. Okay, now this voltage divider bias circuit is the most stable of the three biasing basic transistor biasing techniques. Okay, so for any difference in the beta value, you have the correct stable output. Okay, hence the voltage divider bias is most widely used biasing technique for the transistor. Okay, okay students, thank you for listening to today's class. We'll continue in the next class with the further topics of this module. Thank you.